Nebula are giant clouds of gas and dust that gather in space due to gravitational attraction and, in general, the direction they're traveling. They start to gather in large pockets of space, and you get giant clouds that we see through our telescopes. These are actually stellar nurseries uh, because they give birth to stars, which we'll learn about in a bit, just like our own star, the Sun. Now, what's interesting is that these stellar nurseries also come from star deaths. As stars die, they start to outgas a lot of their material into space, and we actually see what we call planetary nebula through our telescopes, with the rings of ejecting material coming around a star. That gets ejected into space. The supernovae are even more violent because they're a violent explosion, and they actually create the heavier elements. So, in order to create large heavy elements through nuclear fusion, you either need to have a really big star, and in a lot of elements cases they can only come from supernova. So that ends up enriching the interstellar dust and clouds. Okay, so when they start to form into these regions where all this material starts to gather, gravitational attraction starts to pull them together and to form little protoplanets and proto stars. So our sun came out of a similar type of cloud, and this is what my poor drawing of an early nebula of the nebula early in the formation of the solar system. So all this dusted material, which I have drawn brown and some blue and some green to indicate different types, they start to gravitationally attract. Well, that gravitational attraction tends towards the center of mass of the cloud. So most of the objects end up getting initially drawn towards the center of the cloud. At the center of the cloud, what then ends up happening is that as it starts to form into a sphere, it starts to get hot because all these things are bouncing into each other and they're creating heat as they start to condense and become a denser and denser and denser object. So it starts to give off heat. It isn't giving off nuclear reactions yet that fuels the stars. It isn't giving off visible light yet because it's not hot enough, although it does get hot enough eventually, I should say. But most of it's in the infrared, and it's radiating. It's a body radiating like a black body object would. So it starts to push a lot of this lighter material that is in the interior, like helium and hydrogen. It starts to push it out towards the outer regions, and the heavier material ends up staying closer to the center. I'll talk a little bit about radiation pressure in the next segment, but just for now, know that that's one of the factors that goes on here. Another very important factor is what we call the snow line. And the snow line I've drawn here is a region where water can condense to form to ice. This may be counterintuitive, as you may have seen sci-fi movies where they go out in space and they take off their mask and they instantly freeze and they crumble and you end up thinking space is cold because there's no atmosphere. That seems intuitive, but if you really think about it, if you're facing directly the sun and you've got no atmosphere to block any of those incoming rays, when those rays hit you, you're going to heat up quite a bit. So the temperature difference in space is quite dramatic. So in the interior of this line, water can't form ice because the radiation is too intense and it heats up too quick and forms a vapor, if you will. So it has to condense into a solid. In order to condense into a solid, it has to be a certain distance away from the center of the hot object of this protostar. So this has important implications as to why we see bigger and less dense planets out here and smaller, more dense planets on the interior. I also indicated on here the CH4 line and the CH3. This stands for methane, this stands for ammonia. This is a region of space where it gets cold enough where methane and ammonia can actually freeze, which then even gives less dense objects, but they become even more interesting, and they form objects in the Oort cloud, such as comets. Even Pluto mostly resides in the Oort cloud, which is beyond Neptune, also called trans-Neptunian objects, and a lot of planet-like objects that are actually bigger than Pluto. There's I think it's Eris it's called. It's even bigger than Pluto, which is out there, which is part of the reason why Pluto got downgraded as a planet. was because there's going to be so many of those. We discover more and more and more the more we look out there, and the better our telescopes get. So there's a lot of objects like that. So here's where comets are and icy worlds, and this ice can be methane and ammonia, whereas interior they can't because it's still too hot, okay, or the radiation is still too intense for it to form into an ice vapor. So initially what happens here is as objects come together, say an object like is coming in this direction, my fist being one, and another is coming in this direction, they get attracted to each other, and you end up starting to get this rotation because one's going one direction, one's going the other, and they get attracted to each other, and they end up starting to spin. The net of all that ends up spinning about the center in one direction. So now, we're going to fast forward a couple of years to this drawing over here in a second, which you've probably been looking at distracting you. But the radiation pressure has now blown a lot of that material out. A lot of the water ice has started to form with that on top of dust grains and coalesce into bigger objects, and we start to see it clear out quite a bit. Now I've got all these little brown dots which indicate little asteroids, and all these protoplanets. There was a lot of protoplanets in the beginning. We don't know quite how many. Models will tell us that models will tell us a certain number or whatever at a certain point, but they're only computer models. But there was a lot in any forming gas and dust cloud like this that forms and condenses into forming a planetary system. There's going to be a lot of protoplanets in the beginning, and then these have all sorts of chaotic orbits, although they still go counterclockwise if we're looking down at the sun, because of that initial angular momentum. So they start to bounce into each other, collide, maybe spit out some more material, form bigger masses. Our moon was actually is most likely created by such an event. So these start to collide and form bigger and bigger objects. And out here we've got some gas giants that are starting to form and really come into form that we know today of Jupiter, Saturn, Uranus, and Neptune. And then out here is where we have those little weird frozen objects like comets and stuff like that. Really bizarre things out here that we still don't know a whole lot about because we're not able to travel there, and the light they give off is really small. So we get more and more information as time goes on and with more powerful telescopes, but this is still a mysterious world out here. This is very mysterious out here. So what we end up having here is near the water line, we get where the asteroids are. This is most likely due to Jupiter not allowing them to go into form with the other planets, and Jupiter ends up kind of keeping them from forming a planet of their own. But the mass of all the asteroids, if you take all the thousands of asteroids and you add up all their mass, they don't even add up to the size of Mercury, so it wouldn't have formed much of a planet in the first place. So what we end up getting is this clearing out, and we start to have things come together, and we start to get more of a shape of an actual solar system, and what you could call maybe a solar equilibrium, even though you never get there, but an equilibrium where everything has sort of worked its way out. Everything has collided, everything has come together, blah, 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 blah. Here I've drawn a side view before I move on to the next poorly drawn picture over here. Here's a side view of when it starts to form together. Initially it was a big round spherical cloud. Well, not necessarily spherical, it started to become a little bit more spherical. But as it started to coalesce like this, conservation of angular momentum, like a ice skater raising their arms, they spin faster, they pull down, they go slower. Angular momentum is really tricky, so we're not going to get deep into that. The physics of that is alone is pretty interesting and hard to grasp. Okay, so I've drawn this little circular, so everything starts to rotate around this. It starts to flatten. The overall disk starts to flatten. So now we'll get to a more almost present day, where the sun is definitely shining, and we get a view of what the solar system sort of looks like at present day, where the sun actually has accumulated enough mass and started the nuclear reaction process that gives its heat and all that light that it gives off of, and actually keeps its boundaries up due to radiation pressure, which I'm going to talk about in a minute. So here is present day, and everything is kind of cleared out, settled down, and we've got our 4 inner planets, our 4 outer planets, and then out here is Pluto and stuff. I know everyone wants to keep Pluto a planet. Sure, I'm cool with that. But Pluto's out here too somewhere, but it's more like these Oort cloud objects. It's very small, and it's very different than these planets in here. So this has a lot to do with that other line of the CH4 line and the CH3 line, or the ammonia and methane line, in actual words rather than using chemical formulas. So then as time goes on, this continues to flatten, and we get all the planets sort of rotating around on the same plane, and we get a few objects like Pluto will be sort of inclined to this plane, but all the objects, or all the other planets, mostly reside on this plane, and this is due to the conservation of angular momentum, and they end up rotating, and this is why they rotate in the same direction. And this is also why the solar nebula theory worked over previous other attempts to understand how the solar system originally formed. So that is a brief overview of my limited drawing skills of how the solar system came to be. And next, we're going to talk about some of the more particulars. We're going to talk about radiation pressure. Electromagnetic radiation can actually impart some momentum onto an object. Because each wavelength of a photon has an associated energy, it also has an associated momentum. We learned a few units ago that the energy is proportional to 1 over the wavelength of the photon, or it's proportional to the frequency of the photon. Well, for each one of those wavelengths, it actually has an associated energy, and it has a momentum that it can impart onto an object. So this has important implications onto the early formation of our solar system, as it blew lighter objects to the outer part of the solar system, while the bigger objects remained towards the interior of the solar system. I should say the more massive objects, the rocky type objects, and the gaseous lighter elements got pushed out to the outer part of the solar system. So we're going to talk a little bit about that phenomenon, which also has implications in stars, because the radiation pressure actually holds the outer shell from collapsing on itself. All the gas on the outer part of the sun or the star wants to collapse towards the center, but the radiation pressure pushes it back outward and keeps the star in a nice spherical shape. It also has implications as far as how we plan our space missions, because over long distances, the solar pressure can actually, the radiation pressure can actually have a big impact on the trajectory, and we have to account for that. Otherwise, we'll miss our target by several thousand kilometers, and I'll talk a little bit more in detail about that in a second. For now, let me just talk about the basic sort of how to view it from a qualitative standpoint. So here I've drawn a small mass object and a large mass object. The small mass object is easier to accelerate because it's got less mass, and so the radiation pressure can give it a big velocity that way, which is why I draw the big arrow. The massive object, it's harder to get to accelerate, it's got more resistance to being accelerated to its change in inertia, and it ends up with a smaller velocity and doesn't end up going as fast as the smaller mass object. Okay, so let's look at this from a sort of zoomed-in view of what's happening here. So let's look at an individual photon. Even though there's millions of photons coming from here, let's look at an individual photon and how it hits sort of this little idealized perfect sphere that I'll call a light element, okay? It gets really tricky when you actually start talking about how to really calculate that and examine that, because how light interacts with matter. Some of it's absorbed, some of it's reflected, some of it's re-emitted. But we're just going to take this idealized case where we're going to imagine like a small molecule as being represented by a little ball. Okay, so here's the light ray, and it comes in with an initial momentum rho I. So we use rho for when we talk about momentum. So this is the initial momentum of the incoming light, the incoming photon, and the object will assume is initially at rest. So it hits this object. So then after it hits this object, let's say we get a perfect reflection with maybe some absorption, and now the light ray has reflected off of the object in this way, and I have drawn this with a longer wavelength. Can you think of why? I'll tell you in a minute. And that imparts a velocity onto the object. So then now this object actually took some of the energy from this from this photon, and now this photon travels away with a lower energy, which is why it's got a longer wavelength. You didn't have to wait long for that answer, did you? So here's the case of a bigger object, which is the same thing. I have an incoming light ray, or incoming photon. It's got an initial momentum. It hits the bigger massive object and reflects back with less energy because it lost some of the energy giving it some momentum and some through absorption. Now this bigger object then has a smaller velocity after this collision. So that's why I've drawn these different velocities at different lengths, because this gives it a bigger velocity to the smaller one and a smaller velocity to the bigger one. So this has implications as to why the smaller elements get pushed way out into space. And one other thing to notice here is if you're talking about forces here, we're going to look at the force on this object. It's got a force of gravity. It wants to be pulled towards the sun. But now the radiation is giving it a pressure in the other direction. And so what I end up getting is a situation where the radiation pressure, in order for this object to not go into the outer solar system, it has to have, in order for this object to go out into the outer solar system, it has to have a radiation pressure. The force from radiation pressure has to be bigger than the force of gravity on the object. So with lighter objects, the force of gravity is heavy on it, so it can be pushed a lot more. This balance can be, the force of radiation can be bigger than the force of gravity, much easier. And for a heavier object, it's the other case in which the gravity is stronger this way, and the radiation pressure has to be larger for it to accelerate it beyond out into the outer reaches of the solar system. So that's sort of a microscopic view, but I think it might be a little bit easier to picture this when we talk about solar sails. So one of the proposed mechanisms for space travel is to build solar sails that capitalize on this radiation pressure. I talked about how if we send an object into outer space, we have to account for that radiation pressure, otherwise our trajectory will get blown off course. So I have drawn a little schematic over here of a golfer. So here I have a golfer, and he's accounting for the wind. So this would be like the solar radiation that's pushing on the object I send into space. So in order for a golfer to get to that target, they have to aim to the right of the flagstick so that the wind, as it pushes the golf ball, will push it in the direction towards the flagstick. And that'll give it a trajectory that comes to the right a little bit, so they aimed it right, and it comes back to the golf stick. So, or the flagstick, sorry. So this is just like a conceptually on how we have to change our trajectories when we talk about spacecraft, when we send them into space, because we've got to account for that solar pressure pushing on the object, and we have to go and correct for that when we plan our trajectories. So now we'll look at solar sails here, because solar sails sort of capitalize on this effect. And this really changes the color. I became really blue. All right, there we go. So here I've drawn a funny looking ship with a big sail on it, and this sail has a cross-sectional area that can capture more of that light. So we're talking about individual photons. Now we're talking about cumulative, like we have a whole bunch of photons hitting this. So it hits that sail, and the radiation pressure can actually push it in a direction, which is sort of like free travel, right? I don't need moving parts. I don't need to eject material out of the back to get it moving, and it continues to accelerate because it's imparting a force on it. So the trick is the sails have to be really big, and they have to be really light, and they have to be really reflective, because the more it absorbs, the less of the force, and the more it reflects, the better. So creating the perfect material is really difficult, and the size of these sails has to be huge in order to get any actual acceleration. So I've drawn two intimidating looking equations. These are just kind of but I'm going to derive something for you. So I didn't derive this equation. I derived this equation for you. This is a nice way to look at this kind of thing. And here's the force of gravity, which we were introduced to a couple of chapters ago. So here is the cross-sectional area of the sail, or of the object, when we were talking about that rock soaring in space. I'm simplifying this too, because I'm not accounting for if it hits at an angle or not. I'm having a perfect perpendicular interaction with that. I don't have to worry about the angles and stuff, so I've really simplified this. So this is the cross-sectional area that's being hit by the radiation. This is the power output from the sun, and then this is the distance from the sun. That's at r, and the c is the speed of light. I'm not going to get into the derivation of this. I'm just going to talk about this. And then this is the force of gravity, which is also dependent on the distance from the star. Now they're opposite directions. So if the star is that way, the force of gravity is that way, the force of radiation is this way. Okay, so they're both dependent on r squared. So when they combine their effects, it actually doesn't depend on distance, which is also quite nice. It just depends on that power output from the sun. So here, if I want to build a spaceship that actually operates on a solar sail, I actually have to have the force of radiation greater than the force of gravity, as I talked about earlier. So when I put these equations in here, and I do a bunch of math, which I know you all wanted to see really bad, I end up with this relationship that can kind of give you some scheme. These are all constants, really. This is 2 pi is a constant. The speed of light is constant in a vacuum. This is the universal gravitational constant. This is big M, and I should have pointed that out. This is big M, which is the solar mass, or the star mass, if you will. And this little m is actually the mass of the ship here. So this is the sail with a cross-sectional area A. This is the ship and the sail both have a combined m. That's the mass of the ship, and that's what I have down here. So I get this nice proportionality where I have the cross-sectional area of the sail over the mass of the sail and ship has to be greater than all of these things, which are constant. So what this relationship means is that the larger the area, the more chance I'll have for this to be greater, because this number will be bigger for it to get some acceleration on the ship. The smaller the mass that I have, the better chance I have for an acceleration of the ship. So if I think of these things as little corpuscles, what I'm not talking about if I model, let's say, an atom or a molecule like a solar sail, then the smaller the mass, the more it's going to overcome all these constants over here and be able to be accelerated outward. And that is one way to schematically think about how radiation pressure actually pushes those littler objects out into the solar system better than it does the more massive objects. I shouldn't call them little or big, I should be referring to mass. So all this has an effect on why they have inner rocky planets and outer gaseous planets, but it is also interesting to learn about in its own right, because people generally don't think of radiation actually having a pressure associated with it. Some planets have atmospheres, some planets don't. This is related to what we refer to as escape velocity for a particular element that might be bound to that particular body. For instance, Callisto, Jupiter's moon, is almost the same size or same amount of mass as Titan. Titan has an atmosphere, Callisto doesn't. There's various reasons for that, and it really depends on 2 things: temperature of where the object is located, and the mass that bounds the molecule or atom to the actual planet or moon that's trying to host it. So we're going to talk about escape velocity here. And here I've drawn a schematic of a cannonball. If I shoot it with only a certain amount of speed, it's going to fall back to the Earth relatively quickly. Here's the blue line. I shoot it with a little bit more, but it still falls back to the Earth. The green line, I can shoot it fast enough such that it orbits the planet itself, but that it still doesn't escape. So what we need to do is fire it fast enough so that it escapes, which I've depicted in the red line. And this is actually how we launch rockets into when we launch craft into the outer edges or into the outer solar system or beyond, out to the moon or something. We have to have a fast enough speed that we can escape orbit. For a lot of our satellites and everything, we want to be in a particular orbit, so we shoot it at a specific speed. Not shoot it, but we launch the rocket with that specific speed. And the escape velocity is this nice little relation where r is the radius of the planet. So maybe I should draw that on there, because this kind of has certain implications when we talk about black holes, which I don't necessarily want to get into, but maybe I'll mention it here. But this is the radius of the planet, this is the mass of the planet, and for each given planet, the mass and the radius are going to be different, and so they have their various escape speeds associated with each planet. Now let me just talk a second about a black hole, although I don't want to talk too much about those types of things, but the radius gets really small of an object the higher the escape speed's got to be, or it is. So v escape means the velocity I need to get it up to for something to get away from it, okay? The bigger the mass, the bigger the escape velocity that I need to get an object to. So black holes are really, 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 really compressed amount of mass to like infinitely small that you can't even comprehend really. Well, this when it gets in fact gets so big that it actually causes light to loop around and light can't escape, and that's why we call it a black hole, because the escape velocity is bigger than the speed of light itself, so not even light can escape a black hole, and so we actually don't see light from a black hole because of this reason. So, but for our normal meaning, for what we know from our solar system, the objects we're dealing with are not nearly as compact and not nearly as massive, and not even close, okay? Which is still such big numbers it's hard to comprehend, but it's a little bit more comprehending than a black hole. So, I want to talk about the second aspect of what kind of happens here is, from the kinetic theory of gases, you got all these, in a gas, you got all these molecules kind of bouncing around, bouncing off each other, and they all got different velocities. Some can have huge velocities, some can have really tiny velocities. Well, from the kinetic theory of gases, we can get a velocity of an average velocity for these that's dependent on the temperature and the mass of the particular gas, if you will. Like, not the gas, but the individual molecule. So say you've got a gas made up of hydrogen atoms. The mass of the hydrogen atom is what would go in the M there, and the temperature is going to be in Kelvin because that's what we use because it's the absolute scale. So this has a relation to this, in that this is where depending on a star's location, it's going to have a certain temperature. Depending on a star's mass and temperature, or depending on an object's mass, it's going to have a certain escape velocity, mass and radius. It's going to have a certain escape velocity. So this has to be, if this is larger, significantly larger actually, than this, then that planet can't retain the particular element. So if I'm talking about hydrogen, let's just talk about an individual element. If I talk about hydrogen, this is going to be its average velocity, okay? If it's fast enough, it can be bigger, or it can be as big as this number, and then it can escape into space. Now, I said if it's fast enough. So this is the velocity that the average velocity is. But that means there can be ones with much bigger velocities and ones with much smaller velocities. The big ones are the ones that can actually escape, because a rule of thumb, I don't know where that phrase came from, a rule of thumb, it's probably due to construction, I imagine. Anyway, the rule of thumb is that if V average is, let's just say, okay, let's just put this relationship here. The rule of thumb is that if 6 times the velocity of the average, that would give us an estimate of our largest, most fastest moving molecule. I should have drew one 6 times the size of another one, but so if this is 6 times the velocity of average, that will escape into the outer solar system, and that planet will not be able to retain that particular atom or molecule. So this is what I'll call the rule of thumb. Now, what I have is over here is, in a second, is going to be a nice plot of this, and I'm accounting for this on this plot idea here, that 6 times the velocity average is going to allow that element to escape. And this is, I've drawn a nice little way to try to kind of interpret what's going on here, okay? So I've drawn sort of, if I calculate that, actually I can just shift that. If I calculate this over here, if I calculate this number over here, then for each one of these temperatures along this whole temperature gradient, I get this curve, okay? If I calculate the escape velocity for a planet, and I post it vertically on this axis, I can get this nice little plot here, because each planet's going to have an associated temperature, an average temperature that it has, and an escape speed proportional to that, and this is going to be the average speed times 6 that it would need for it to be able to hold on to a particular element or atom. So if I have planet A here, which is a really hot planet, so this would be something like Mercury or something, which is really close to the star, and it's got a really low escape speed because it doesn't have much mass. Okay, so its low escape speed is really low, but it's still CO2 throughout, no matter what temperature gradient I am underneath here, no matter what planet's going to be in this region, it's not going to be large enough, or it's going to be too hot to be able to hold on to CO2. So this is why Mercury doesn't have an atmosphere, because Mercury would be somewhere in there. Our moon would be somewhere in there. Callisto is somewhere in there. So that's one way to look at this, because this is for all the various temperatures across these and for all these escape speeds, this is sort of a region in which it can hold on to CO2. I can go up to the next one. O2 and N2 kind of have the same amount of weight. They're really close to each other. So this is nitrogen and oxygen, molecular oxygen, molecular nitrogen, which is what we find in our atmospheres. And this would be that line of that calculating that velocity average and then multiplying it by 6. This would be that line. So planet B here, which is on the border, which I've calculated for H2O. I didn't calculate, this is a schematic. We will do calculations in the lab. The planet B here is like on the borderline of water. So it can retain some water, but not a lot of water, because a lot of the water will still escape. But it still can retain a fair amount of water. It can retain all the O2 and N2, it can retain all the carbon dioxide, and they won't escape into space. Planet C here, one last thing to mention is that hydrogen, it has no chance. Hydrogen is going to go into space. It's going to escape no problem, because this is the escape speed, and this is the average times 6 of the hydrogen at this point. So I'm going to go directly up to this point. So this is the temperature of the star, and this is the escape speed. That's what gives me that data point. So C here is say a large gas planet like Jupiter, where it's really cold because it's out in the outer edge of the solar system. It's really cold, and it has a really high escape velocity because it's really massive. So something like Saturn or Jupiter or Neptune up here, this planet C, can actually have all of these things in its atmosphere. So based on where the planet resides in sort of this kind of plot, which is just a bunch of relationships at once, which I think is a really nice view of this. If I have a planet here, it can have CO2 in its atmosphere, but it can't have oxygen. If I have it right on the line, it can have some oxygen, nitrogen, and CO2. If I plant it up here, it can have water, oxygen, nitrogen, CO2 in its atmosphere. And maybe if I put it right on the line, it can have just a little bit of hydrogen too. So it all depends on what the average temperature of that object is and how massive it is and what its escape velocity is, because each of these will have an average temperature based on an average velocity based on the temperature of where that is located. So this is a really interesting aspect as to why some planets have certain atmospheres and others don't. We've learned that particular elements get pushed out into the solar system, so they are available to form those in the first place. So there's a lot of different variations that we can get on planets, their atmospheres and their composition based on a number of factors, and we just took you on a grand tour through all those factors. The physics of these things gets pretty crazy because there are so many millions and millions of interactions, and we're talking about macroscopic behavior of millions of atoms and millions of photons. So it gets really hard, but schematically it all starts to make sense from a solar nebula standpoint, and in general gives us a very, very rich, diverse solar system to explore, and also would relate to when we can actually start studying exoplanets. We're going to see a tremendous variety around other stars as well.